All right. Hello, everyone. Good morning if you're joining from my side of the planet. Good evening if you're joining from one of the other sides. Um, I'm Charles. I'll be leading the Modal webinar today. I'd love to hear where folks are joining from. It's I think, a cute little ritual we do in these kinds of webinars to give a couple minutes for folks to trickle in as the session starts. So I'd love to hear. I'm in San Francisco in Modal's office here in the Northeast Mission District. I'd love to hear where other people are joining from. I see a lot of waves in the chat. I'll take that as a hello as well. Um, yeah. Okay. Yeah. Some folks from Canada, Florida, Long Beach, another Californian, if it's the same Long Beach I'm thinking of. And yeah, so we'll be talking today about Modal's serverless GPUs. By the way, so you should be able to see my screen. Let me double check that. Actually, I think you can only see me right now. So let me boom bring in the slides. So now you should see my slides on truly serverless GPUs. Great. So while I was doing that little bit of AV, we got some more folks coming in the chat. Seattle, Berkeley, Palo Alto, lots of California representation. Georgia, Vegas. Oh yeah, some folks from Europe. Oh, Michelle joining from Brazil. I'll be in Rio shortly. We sponsored some stuff at the upcoming iClear conference. Thumbs up in the chat if you remember iClear when it was only 200 people a decade ago. Yeah, time flies when you're building artificial intelligence. That's my experience. Great. I'll maybe give it 1 or 2 more minutes before I dive in on the stuff today. I guess I'll just get a couple little bits of logistics out of the way. So yeah, these webinars are recorded, so the recording will be available afterwards. We'll also post it on social media, on our YouTube channel. You can find us there. We're Modal on YouTube. And the slides are also available. If I think Felicia's here helping me out run this webinar. Felicia, if you could share the link to the slides in the chat so that people can read those. And you'll also this is something of a sneak preview for the folks who are joining now of a blog post that'll take all this stuff. We're going to go through some nice technical details here, and so we'll have a written version of a lot of this material in the next couple of weeks that will have all the nitty gritty details and links to sources where you can learn more for folks interested in that. All right, so that 4-minute delay has doubled the number of people in the audience. Welcome to everyone who came in the last couple minutes. Hope you've got your coffee if you're here on the in the western side of the Western Hemisphere, or your nightcap if you're one of the folks joining us from maybe Switzerland or Spain. Let's settle in and let's get going. All right, so what are we talking about today? We are talking about something different from what we do in many of our other webinars. This webinar series is a lot about sort of building stuff on Modal and how to use Modal. We've talked about speculative decoding. We've talked about reinforcement learning, things that you can do using Modal. This one's a little different. We're going to talk about how we built Modal and why we built it that way, and some of the technical sort of approaches and the technologies that we've used to build Modal, to sort of explain why the system works the way that it does. So, and maybe why we think it's such a good idea, and why we hope you'll either want to use it and build stuff on it, or you want to join us and help us build it. So I'm going to start by answering the first question. So the title of this is truly serverless GPUs. So why should somebody care about serverless GPUs apart from just being a huge nerd like me for making computers faster? So the core goal here is to maximize your GPU allocation utilization, and as an engineer building a system to match the supply of resources that you are paying for with the demand of resources for the application you're building. So let me go into detail on what I mean by that. So the key thing about inference applications that's quite different from training applications, if you've been a machine learning engineer for a while, is that inference applications have variable demand. So this is a little bit of data that we simulated on the basis of some customer data on the number of requests that a service received per minute over the course of a month. And so you can see this sort of variability over time. So there's kind of a daily cycle you can see, and maybe some decreases on the weekends, increases during the week, pretty common for maybe business sort of productivity oriented software services. So you see there's the number of requests that this thing is getting per minute has a peak to trough difference of a factor of 2, 200 to 100, or maybe even 400 to 50 over the course of the day. So in addition to that kind of variability, which people are maybe a little bit more used to planning for, there's some tools you can use to handle it. You also have this kind of variability that comes from maybe the increasing adoption of your system over time. People are building companies and building services faster than ever, driven by the ability to distribute your service really quickly via social media or other networks, and also the ability to sort of ship features and drive increasing demand really quickly, thanks to AI agents and other productivity increases. And so you can see demand for this service goes up to 1,200 requests per minute by the end of the month, after starting at 100 and so a 10x increase. And so the demand for your service can massively change. It could go up on holidays. It can go up when you hit the front page of Hacker News or Product Hunt, or some influencer talks about you on TikTok. And this variability in demand is a real challenge for engineers. You need to be able to service that demand within some SLO, effective SLO maybe, of we want to respond within 1 second. But if you want to be able to service that demand efficiently, so you also want to not spend, not break the bank servicing this highly variable demand. So the dilemma that you get put in, especially with really expensive hardware like GPUs, is you get caught in this dilemma between trying to the easy thing to do, especially if you have a giant pile of money, is to just buy a bunch of hardware to service your problem. So make a fixed over-provisioned allocation of GPUs. And that's represented by this pink line here. And then at any given moment, you're probably not using most, or you're probably actually using only a small fraction of what you've allocated, because you need to allocate in order to handle these big peaks. So something this, the proverbial, hug of death from Reddit. So you've over provisioned in order to handle that. You're paying for all of that compute the entire time, but you're not using it most of the time. So this happens quite frequently when people go through a classic cloud reservation or a rack and stack co-location approach to handling GPU compute. So this is pretty wasteful. And then even worse, you can see it's hard to predict what what your peak demand is going to be over the course of months. Sometimes it can be hard to predict what the peak is going to be within a given day. And so you will often miss it. And then during that time, you're also going to miss out on your SLOs. So this, the solution is not, one solution is to try to automatically allocate resources in response to demand. And this is tricky with GPUs for market reasons. If you've tried to get a hold of 8 or 16 or 32 H100s or B200s, you may have discovered that you can't just easily get a hold of them for 10 minutes or an hour unless you're using Modal. And so there's sort of these market dynamics lead to these long-term reservations, depicted here, being your primary option. But let's say you figure out a solution to that, The next problem that you have is that you need to be able to rapidly allocate and deallocate resources in response to rapidly changing demand. So by default, it can take like, tens of minutes, maybe even an hour to like, go through the cloud provider APIs, find available instances of the type that you want in a region that you can run in, spin that machine up, like quality check it, and then spin up your application. So all that time that you spend doing that setup is time that you are not able to service the application demand. And so that leads to this phenomenon that you can see in this depicted in this graph here, where it's like your allocation lags on uh, the demand as it comes in. So the sort of speed here, you're like you have two problems, right? First is that you're going to lag when demand spike comes in, which for really fast demand spikes means you can just like miss the entire thing. And then the other thing is that you will end up over provisioning a lot because you'll be like loath to let go of a machine that takes you a long time to spin up. And so that that you end up with the same problems that you have with an over-provisioned allocation. Then this automatic allocation, if you can make it fast enough, then you can handle this variable demand, and you can pay for exactly the amount you need and hit both your slower variations in demand and your your peaks. If you could if you could spin up new instances of your application really very quickly, and then you can spin them down as soon as they're not needed because you know that you can spin up a new replica when you want. So it's one of the key goals with Modal. I think I might skip this slide to sort of move a little bit faster. But the kind of like key point here is that if there's a kind of a limited supply of GPUs, and the more efficiently people can use GPUs, the better. Like there's like more demand than there is supply, and if everybody tries to handle their peaks with this like over provisioning, then we get a lot of wasted idle GPUs. But if people sort of do this automatic allocation in a multi-tenant sort of pool of GPUs, then you end up with like a much lower fraction of unused GPUs. So yeah, that's what we've sort of built Modal in part to solve this problem, to get we've got this like pool of on the order of tens of thousands of GPUs across on the order of 10 different cloud providers that people can use to like execute their like build applications that automatically scale with really rapid allocation and deallocation of their GPU resources, along with everything else that you need to make the application run: container images, volumes of distributed storage, dictionaries and queues for distributed communication. So that's what that's sort of the system that we've built to solve this problem. And I see some hearts in the chat. Maybe somebody from one of the teams whose logos up on this page is here. Yeah, we've got lots of folks, right, ranging from big teams at places like Meta to AI native startups like Lovable and Suno building applications on the platform. And in order to solve this problem, we have had to sort of build the stack from the ground up and sort of not use any of the kind of existing tooling that tries to solve these problems. So we don't use Docker containers. We don't use Kubernetes to manage the allocation deallocation of instances of work, and we don't use and we also don't use like a job manager like Slurm that people frequently use for training clusters. We found that each of these technologies has kind of some built-in assumptions that don't quite work in this in this world of rapidly changing demand, of heterogeneous hardware, of inference and artificial intelligence applications. So I'm going to talk you through the stack that we built to solve these problems. And sort of how we essentially optimized the startup latency for both containers, the sort of underlying machines and containers, and also the like application code that you write that's to get that to start on Modal as fast as possible, so that you have this truly serverless experience. So actually, yeah, can I move my head over to the other side? I think I can't move my head to the other side. So you can't see the end of my quote down here. But this quote here is from Hansen and Crane. It's in Brendan Gregg's performance engineering book. It's kind of the essence, I think, 3 mantras that are part of the essence of performance engineering. Don't do it, but never do it again, and do it when they're not looking. Each, these are kind of the tricks you use to take latency out of a hot path and sort of speed something up, and unlock a new application. Okay, so the fundamental problem, I'm going to use this diagram throughout the whole thing, so I'm going to walk through it a little bit in detail. So the whole process of finding a new machine, like allocating it, health checking it, getting the operating system image that you need on it, and then getting a container up and running, starting an application, starting inference on a GPU, and then being ready to service a user request. That's what's represented by this bar here, and it can take up to 30 minutes. It depends, obviously, on the details of what you're doing, but this is something we see pretty commonly for inference applications. So if you want to imagine a specific application here, imagine getting a hold of, a B200 server to run, say, the new Qwen 3.5, 36 billion parameter mixture of experts model. And so there we have this timeline on the right for our about 35 minutes or 2 kiloseconds of startup time. The colors there represent different sort of components of the machine that are, sort of the load-bearing piece during each of these periods. So over here, this is sort of like a little diagram of a computer that I made, a sort of cartoon. So the gray is like the machine. So we have gray for like getting a hold of a machine and allocating it. And then each of these little sub boxes are the components of the machine. So we have the CPU in blue and its memory above it. And that is connected to a GPU in green beneath it. So that you can see the little bars to connect these components. So the memory of the CPU can talk to the memory of the GPU. Those 2 things, that memory is an important place where state is accumulated and stored, but sort of more durable state is stored in the disk that's in purple there. It's an SSD, but we got like a little ARM and disk on it because that's the classic sort of diagram. So that stores longer term state. And then since we're doing this kind of like cloud deployment with ephemeral workers where we're sort of like spinning up replicas and moving them around, actually that disk is something that is like not our sort of bottom level storage. So we communicate with some external storage, cloud resources for storage, databases, object storage, what have you, and that's represented by this little white drum out here. And we communicate with that through the network interfaces like the Ethernet interface or an InfiniBand interface. That's represented here with this as this orange network interface card or NIC. And that is, we won't talk too much about that because it's not super critical here. It's not a place where state accumulates, and state turns out to be the really tricky piece. So yeah, there was a question just to remind, this gray part of the diagram kind of represents the machine here. And so it's sort of, in the diagram, it's just a box to hold the computer together, and gray in the timeline represents time that's spent sort of allocating and health checking and setting up a machine in which you can then do your application-specific setup. So this will all become clear as we go through. I just wanted to sort of walk through this before we start talking about the specific components. Okay, so like by default, if you just use off-the-shelf components, you set up Kubernetes and Docker, you talk to the cloud APIs, you start running your vLLM or SGLang server. It'll take you about 2 kiloseconds, and we're going to talk about how we drop that to like under a minute, 1/20th of a kilosecond. So the basic flow here is, so on the left is what you sort of would do by default, and on the right is what we do. So the default is, okay, you need a new instance. All right, let's spin up a new instance. You need to start a container or a VM, so you need to get the file system for that present. So you eagerly download that file system, and then you start the application on the host. And then once that has started going, the GPUs are attached, and then you start the application on the device, and then you're ready to start servicing requests. What we do in Modal to give you this serverless experience is we maintain a buffer of instances ready to go. We lazy load the file system. We fetch a couple things ahead of time, but we generally lazy load the file system so a container can start before the whole file system is present. Then you can opt in to snapshotting to skip these last 2 steps. So instead of starting your application, we can just restore the state of a Linux process. And instead of starting your application on the device, we can restore the state of a CUDA context with our memory snapshot system. So we're going to walk through the performance optimizations on the right here with pretty much the rest of our time in this webinar. All right, so we'll start up with the spinning up a new instance and how we get around this by maintaining a buffer. So in this first big chunk of time, you need to sort of allocate a machine, boot an operating system, make sure things are generally healthy, and then do anything application specific after that. And the time this takes depends on a lot of factors, but 10 minutes to tens of minutes is a pretty good estimate. So the trick here is to remove instance start from the hot path by running a buffer of instances that are ready to go. So in this case, I've shown here, these are all little tiny machines. This is a tiny version of the diagram we saw previously. So 5 of them you can see are a little bit darker. Those are ones that are already running application code. They're already full up, let's say, and then 3 are empty. So we have a buffer of 3 machines that are ready to start running applications. So then when a request comes in that somebody wants to allocate these 2 GPUs, let's say, to their server, we just start running we start setting up their application on one of the GPUs from the one of the instances rather from the buffer. So now they don't have all the work to sort of acquire the instance, make sure that we have availability for it, health check. These things all happen sort of outside of the hot path, and then our buffer has shrunk. So maybe we want to run a buffer of 3 to 4 GPUs. So then we start grabbing a hold of 3 or 4 instances. And so when we have only 2 instances in our buffer, we increase the size of the buffer. And then and so then we can sort of handle these requests always from the perspective of the user. They get super short latency because you're always servicing out of the buffer. The sort of downside on this one is you can never get 100% utilization if you're maintaining a buffer, but 100% utilization is kind of a mirage. It's a little tricky. And so it's really nice actually to live your life with a buffer. Let me say this, have an extra toothbrush at the office and one at home. You never know when you might need to clean your teeth. I got carry a portable charger, and I have a charger at home and chargers in places where I spend time, and sure, it causes a little bit more expense because I have multiple chargers, but I get to live a much more convenient life, and you avoid the crunch of not having power. So having that little buffer is really nice. Yes, always be buffering, says Amashi in the chat. So yeah, Frank asks, how much of a buffer do you usually have? Can I always start up hundreds of GPUs, say B200s? So for this varies. It depends on like how much load we have. It's sort of a fractional buffer, and the sort of the things get sort of like split out by region, so it's hard to answer sort of that question super directly. But I will say that in general, if you wanted to start up maybe hundreds or thousands of machines, you might end up like we would probably end up needing to scale up instances in addition in order to service that. But if you have an application where you want hundreds of or thousands of GPUs, including B200s, talk to us and we can ensure that your demand is satisfied. And so there's some great questions in the chat. I'm going to scooch forward a bit to make sure we get through everything. But yeah, so you start off with this, sort of 2 kiloseconds of delay, and by you replace this big chunk at the beginning of instance allocation with basically just like a database lookup and a little bit of routing, and so it basically vanishes, and you're down at 1/3 of a kilosecond or 5 minutes. So yeah, so moving forward, I'm going to expand that bar out. So now the full length bar here is 300 seconds. And so the instance start is that little tiny gray piece at the beginning, and that'll allow us to see these smaller bits a little bit more clearly as we go. So this is a pretty big win. One key component to make this work really well is health checking, especially because of GPUs. They're like quite a bit less reliable than other hardware. They get run like very close to their like thermal design power. They are sort of pushed to the limit. NVIDIA is kind of pushing these machines as hard as they possibly can. Sort of like the there's not much wiggle room with these things, kind of like an overclocked CPU. So they have kind of failure rates that are more reminiscent of like a spinning disk, or maybe even worse than that, actually. And so they require this kind of like health monitoring. So we talk a lot about our health health checking system in this blog post, and sort of how we give this like very smooth like guaranteed high quality kind of experience with these instances like that we're giving out to folks. Oh, I forgot to include a slide on this, but we also have a blog post where we talk about the process. Somebody asked whether this like buffer is sort of like automatically scaled and managed. And we talk about that in our blog post, Linear Solving for Fun and Profit, which talks about the linear solver that manages the sort of construction and maintenance of this pool of instances, including the buffer. And that blog post goes through it in detail. So I won't say too much more about it because I don't have any slides on it. And oh yeah, Siddharth asked, you maintain an image-specific buffer pool as well, or is it just at the machine level? If I'm running a serverless application, do I get a user-specific buffer? So that is something you can configure buffer containers. Like we run this buffer, for everybody. It's a system level thing. But also like the general idea of having a buffer is good. And like you can take some of this like application-specific setup and move it outside of your hot path. By running your own buffer. And so for that, we have buffer containers on your function decorators. So check that out to do that, to sort of like operate your own user-specific buffer. Of course, the difference there is like we take on the cost or the risk, if you want to think of it that way, of like the modal level application, the modal level, like sort of system level buffer, your application specific buffers. Since you're using those GPUs, you sort of like take on the costs there. But that's really nice for sort of like managing, sort of adding some cushioning to these like oscillations up and down. So question from Shaq, if the buffer underruns, does that mean a user waits 30 minutes for a container, or does another customer get preempted? So the answer is neither. So you end up queuing for a container, right? And so like just because all of these are, I depicted this with sort of like, somebody grabs the machine and it stays being used the entire time, but actually like some people are running like a quick, shell, or um, uh, they are like running a quick benchmark, doing some development work. And so they like grab a machine for a few seconds and then drop it, or a few minutes and then drop it. So at any given moment, the like users are turning over on the, many of the machines that are already allocated. So you don't have to worry in general, like you wait, for a single GPU wait times on Modal are essentially like queuing times are, like 0 in P95. I'm pretty positive across all our GPU types over the last like month, thinking of some internal metrics dashboards that I've seen. Okay, so lots of great questions on this. If you find your question wasn't answered, like please DM me on Twitter or in the Modal Slack. If you want to follow up on a question I didn't answer it, I do want to make sure that we have time to talk about the whole system. Okay, so we started off like first trick, maintain a buffer. Next trick, we need to set up the sort of file system state. Let's find a more efficient way to do that with some lazy loading. So we now have our little 300-second startup period. There's this purple chunk at the beginning here. What's happening there? A container is being started up inside the allocated machine, and this can take, let's say, like a minute or two. And during that time, all you're doing is sort of like setting up the file system so that the container can start running. So a container image, the thing that you need to do in order to start a container in a default kind of container runtime is like get the container image present on the machine so that the container can start running. So the container image is basically a root file system that you can run inside of another root file system. So you have your root file system on your machine that has, bin and users and things like that. And then somewhere like if you have like a container image on that machine, somewhere else you have another root file system that also has, a bin and maybe some users, and then like the code for the specific application. So traditional container runtimes are going to load this file system eagerly, layer by layer. So you build up this container image in using something like a Docker file. You build this up sort of layer by layer by describing like a set of changes from some base. And those get stored as a bunch of zip archives. And then in order to reconstruct the image, the sort of typical thing to do is to load each one of these sequentially and decompress them and layer them on top of one another. And so that's sort of, you can see that's like these layers are getting turned into these components of that root file system. So you like, and these, an operating system distro, including all the libraries you need, PyTorch and the whole CUDA stack, all this stuff. This is going to be many gigabytes, and you are going to be like, loading and decompressing them like relatively slowly at maybe 100 megabytes a second. So this can take like, seconds to or longer to spin up. Yeah, like 100 gigabytes is totally reasonable, and that's 100 seconds at 100 megabytes a second. And this is actually like kind of wasteful, and there's a paper about this called Slacker from about 10 years ago that talks about the problem that like if you look at the like total size of some container image, it may in this case they range up to a gigabyte. But when you actually like run the code in that container, the amount of it that you read is down in the low like tens of megabytes, maybe 100 megabytes most of the time. And so actually like the majority of this stuff is not that useful. And so you're doing all this work loading this the components of this file system for no reason. So we wrote this custom file system based off of Fuse file systems in user space to load images asynchronously. So we load just, there's a little bit of like metadata that you need to load. So that stays as like a couple of seconds of maybe at the most, a couple hundred milliseconds at the start of loading. And then for everything else, we load the file system asynchronously. So that can either be done lazily, sort of like on demand at the moment that the user application requests it, or we can also sort of do it asynchronously apart from the container startup so that it's available, later when the user application requests it. So that's represented by these guys here. So we're like loading, we immediately start loading some stuff. And we load, everything that we think the application needs. Then it needs something else, so we start loading that. Yeah, and there's maybe some quick reads at later points. So the key technology here is Fuse file system in user space that allows we implement the backing file system for this in user space instead of inside of a kernel module, which makes it the key reason here to use this is it's much easier to develop something that say talks to a bunch of cloud storage as a user space module as opposed to as a kernel module. And so that, this allows, really rapid feature development and iteration with essentially no impact on total throughput, which is kind of the key metric here. And some minor impacts on latency for fast reads. So we generally, you wouldn't use this for terminals or those kinds of character devices. So this technique takes something that might take about 300 seconds, 5 minutes to get started, and chops off that whole container start time about a minute, 100 seconds. The key performance component here is that we sort of break things down into blocks. We and store blocks in a content addressable manner so that if multiple container images that have the same content in them, even if they're located at different locations or if they're in different Docker file layers because the person has a different image definition, we can still share them in this in a cache. And so we can load them from lower latency, higher throughput storage that's closer to the container instance. So this cache here, by the way, is what this is maybe a bit of marketing terminology, but I like to think of it as a cloud native cache. There's all kinds of caching going on inside of your machine, like the Linux page cache. There's the caches inside the GPU, inside the CPU and the GPU. And if you want high performance applications, you need to write your applications to be native to that cache. In the cloud, there's a similar stack at a much larger scale of caches. So you still have the things that are available on your machine. So the Linux page cache is a key target for us to get stuff into the page cache so that things are serviced as quickly as they would be, as quickly as they can be. We use really big disks on our workers so that we can store lots and lots of these content addressed blobs so that most of the time, most of the stuff that you are going to read is, already available on disk. And then the capacity of those are limited. There's a wide variety of workloads people are running. So we cache things in availability zone cache servers in some cases, but we especially like to serve them out of regional CDNs and out of blob storage. That being the bottom layer of the cache that gives you your durability and the highest latency, maybe the lowest throughput in some cases, but gives you your total backing storage. And so one key performance detail is there was a lot of pieces required to get this to run performantly. One key detail here was that we needed to tune the read ahead in libfuse, which is when you request a particular page, the kernel can go ahead and like also issue requests for future pages to store in the page cache, and the sort of default behavior was like left some performance on the table, didn't allow us to hit like the peak throughput. The maximum was way too big, and so in between we found this that like 32 megabytes, which is, I don't know, 8,000 pages, I guess, at 4 kilobytes a page. That was the right amount, because people tend to be loading like large large binaries, lots of things sequentially. And yeah, this is a question in the chat. Yeah, this was determined empirically. One last piece is compression seems like a good idea, but the sort of default compression gzip is single threaded. We don't necessarily always control the image construction process, so we can't always like control the compression used. And it reduces sort of compatibility between different forms of tooling. So it's actually better. The like throughput on these things is actually quite large, and the like storage capacity of something like blob storage is effectively infinite. And so it's generally better to, in our experience, to run with like uncompressed versions of images. Be nice, maybe, done some explorations of more modern compression algorithms, and there's some places where we take advantage of better compression with eStargGZ or eStargs. But in general, you don't have this, and the like the old school algorithms in gzip like Lempel-Ziv, Huffman, these things are like inherently single threaded, can't be made faster. So folks are asking about like preload optimizations and sharing cache peer-to-peer. Preload optimizations we definitely have based off of task profiles. So yeah, your starts will actually get faster on Modal over time as you deploy over the first couple like container starts. For model weight loading, we'll talk a little bit more about that. The answer is not like the generic optimizations that we use already work for model weight loading, nothing special. And P2P cache sharing is sort of like on the roadmap, and there's some exciting stuff here. If you want a lot more details on how exactly we built the system, this component of the system, check out this talk from our engineer, John Obalati. 1 second. I am, speaking of running a buffer and being short chargers, I am short power. Give me 1 second. All right, I told you, carry a portable charger to make your life a little bit better. Here it is. Buffers in action. My little power buffer here. Hopefully that should keep me going for the next 15 minutes for the rest of this presentation. All right, so now let's talk about some of the. Actually, I just realized because I'm running low on power, the system's going to divert power away from things like the camera and streaming. So I'm actually probably going to need the full wattage I can get from a wall charger. So apologies for this. I'm going to need 30 seconds to run and grab my proper wall charger. Oh, never mind. There's one hanging here. All right. Exciting times. All right, so yeah, computers. It's hard to get them to be reliable and to work perfectly. But if you carefully design redundancy into your system with buffers and spare chargers around, then you can manage it. All right, back to container starts. All right, so what happens during this little blue phase here? We've got the container running. User code running inside the container is going to create, basically create a bunch of processes and threads within processes to start their application and get it ready to service things. And the key insight here is that in the end, a process is also a data structure. It's a stack, a heap, registers, some kernel data. And so what's going on during this sort of initial period is essentially the creation of some data structure that you can then that is running a server, for instance, that you can set that and that this data structure backs the execution of that server with the memory allocations, the TCP sockets, all this stuff. So the key insight is that we want to store that data so that we can skip the work the next time that we run this application. So we can sort of checkpoint, take a checkpoint of what that in-memory data structure looks like, store it in our cloud storage system, and then the next time we need to spin up a container, we just restore it. And so we can skip this chunk of work here in all these future requests for the same thing. And for Modal, we really only need, for speeding up like startups for serverless containers, you really only need checkpointing at the time the application starts. You don't necessarily need like transparent checkpointing at any time. It's a cool feature, helps you migrate workloads. We're definitely interested in it, but you can get a lot of utility out of a much simpler kind of checkpointing that users opt into. So if you want to use these memory snapshots, you add them to your decorator, and then you sort of express using some other decorators which components you want to be part of this snapshotting process and which you don't, and then what is your actual sort of application request servicing code. So that looks kind of like this. So the technology that we use is GVisor's checkpoint restore. So we use the GVisor runtime, runsc, instead of the Docker runtime, runc. And the key thing with GVisor is it basically runs like it sort of emulates the Linux kernel in user space and sort of offers a limited syscall interface, so fewer syscalls than the host kernel supports. And so this sort of emulated kernel is something that can be checkpointed. We just take all of it, all of its data structures and persist them to disk. If you poke around in a runsc checkpoint, the main thing you'll find is a pages.img file, memory pages. Like that's the core data structure you need to store, and that is what we store in our cloud storage and then restore from later. And as like a tiny aside, GVisor, it's written in Go, so which has this sort of like non-preemptive cooperative concurrency model. That means it's essentially already a state machine with safe yields all over the place. So there's points where you sort of like the control is yielded, and so it's like actually quite easy for GVisor to support this kind of like checkpointing and restore transparently, and that that makes this relatively straightforward. There's also support for this via CRU in the Linux kernel, but that's like quite a more complex system. So the key performance target here for making checkpoint restoration really fast, so making boots really fast, is this restoring pages.img. So like getting it sort of like out of cloud storage onto disk on the machine, so that it can then be like these pages can be like put back into memory. And the nice thing is like the same system that I described for our container images also works for these memory, this like disk representation of memory pages. And so the exact same sort of combination of disks, like the raw worker page cache, all the way up to blob storage. The same system also helps load these like pages.img files, these memory images or checkpoints or snapshots really quickly. So this takes, that like initial sort of host side startup takes a few seconds, like maybe a few, like 10 seconds or so. So that can take something that takes 200 seconds to start and really kind of keeps it at about 200 seconds to start. So the win here is not the like sort of raw performance benefit from the host side snapshotting. And the like key reason for that is that this host side snapshotting or CPU side snapshotting has like, you can't do anything on the GPU while you're doing this because the GPU has a separate, sort of memory store in its RAM here, right? And that is not being captured by this system by default. So it doesn't give you a big win for this inference server case. I'll say that there are like some specific micro benchmarks and even some workloads where a lot of this like this like overhead at the beginning of doing something like importing Torch, which is like tens of thousands of syscalls and can be sped up. That can be sped up from like 5 to 10 seconds to 500 milliseconds to 2 seconds, and that so there are like some wins on specific simpler applications or on some benchmarks, but the key unlock here in my mind is actually especially if you're thinking about like serverless GPUs as the goal, is that if you can't snapshot and restore the host, then you won't be able to snapshot and restore the GPU. So that's the last thing that we do. We bring the same idea of like skipping application start and replacing that with restoring this like Linux process data structure with replacing starting application on the device with restoring the sort of CUDA context. So what's going on during that like couple minutes of start time with something like vLLM or SGLang is your application code is creating CUDA resources inside of a context on the device. There's like things like CUDA graphs, there's JIT compilation, so there's like actually resources both on the host and on the device, but they sort of like cross these two things. And so the CPU only checkpointing doesn't help you here. So the key idea is, again, store that data so that we can skip the work next time. So we have all this work that we have to do the first time. When we get to the end of it, we checkpoint that, put it into cloud storage, and then restore directly from that cloud storage, and so save a bunch of time. So the key tool here is CUDA checkpointing. So there's there's both a CUDA checkpoint binary, an application, and then also features of the CUDA driver, the CUDA runtime and the CUDA driver API that support this kind of checkpoint and restoration. And the implementation is kind of cool. The idea is to like ride on top of this existing host checkpointing technology. So CUDA checkpoint will take all of the sort of data structures and things present on the GPU and like driver state, etc. And if you call CUDA checkpoint, then it will move all of that information out of the GPU memory and into the host memory. So into the CPU memory. And now that it's in the CPU memory, you can use the same checkpoint restore system to then move it from memory to disk, and from disk to wherever you want to put it in your in the tiered like cloud native cache, the like storage system. And then when you restore in reverse. You first run sc restore to get stuff out of the disk and onto the CPU memory, and then you run CUDA checkpoint again in restore mode to move the information that's now in the host memory onto the device. So it's like it's like a Matryoshka doll, or like two sort of iterations of the same process. Sort of neat little trick that the NVIDIA folks came up with for solving this problem. And this is a really big win for inference servers. It can take something that takes like, a couple minutes to start to, vLLM or SGLang down to like tens of seconds to start. And so like another factor of 6 speed up here. Maybe like a factor of 10 is like, I'm being a little bit cautious here and not overpromising, but like a factor of 10 speed up I've certainly seen. So there's some great questions. I will get to them. Just want to finish this section. So the proof of principle here is kind of like skipping over a sleep, right? So the proof of like the sort of ideal program for this kind of snapshotting is something that all it does during the snapshot is just like wait. And so this one, if we have a delay of about 10 seconds, we can speed up startups by about 10 seconds. So pink is the non-snapshot version, green is the snapshot version, and we've sped that up by about 10 seconds here. Another really good one, and is sort of like MVP, is skipping over the Torch compiler. Torch compilation can massively speed up model execution, but it's like hard, kind of impossible in my opinion, to properly serialize and so like cache torch compilation in a way that's like really performant. But with GPU snapshotting, you don't need you instead of trying to come up with a way to serialize and snap and restore the torch compilation artifacts, you just like the whole GPU memory is what you're trying to is what you like store and restore. And so for that, you can get these huge speed ups. I think you can see there's still some cases where in order to like create the checkpoint, you still have to run torch compilation, and that shows up as this like long tail here in your like P99s, but it's the same time that you would spend without snapshots, which is this pink one. And then the vast majority of the time, I think in this case, 97%, if I remember right, is this height here. 97% of the time, it starts like within a few seconds instead of taking about 100 seconds to compile this model. And then this also works for SGLang and vLLM inference servers. You can find sample code for this in our docs, modal.com/docs/examples. Look for snapshot, SGLang and vLLM snapshot. And this can speed up server start from, on the order of a minute to 3 minutes down to on the order of like 10 to 30 seconds. That's the green curve, is the curve with snapshotting. So in order to get, oh yeah, good. I should have known that I included the link in these slides. So that's where you could find the SGLang snapshot docs. Key thing here is that you do need to adjust the server a little bit. You need to add this release and resume memory occupation feature. So you want to spin up the server, then actually drop the KV cache, and then wake the server back up. I think you drop the KV cache and even also the model. And the key reason for doing this is that the performance win is from like skipping over server initialization, CUDA graph capture, JIT compilation, and this also improves a little bit the sort of you get rid of a bunch of device resources that are actually like quite easy to recreate. And so this also improves compatibility. So to be clear, if you read our docs on GPU snapshotting, you'll see that there's some caveats. Like for the torch compile case, there's this environment variable, torch inductor compile threads, that you need to set in order to improve compatibility. So there's like some sharp edges here because GPU snapshotting is relatively recent feature of the CUDA drivers, and many like applications aren't written sort of expecting it. But you can use it for pretty much anything that requires only a single GPU. I saw there were some questions about nickel connections and RDMA buffers. Right now, that's not supported due to limitations on the sort of like driver level support. But we anticipate that coming soon in some future NVIDIA driver releases, which we can then use to support multi GPU and even multi-node applications with GPU snapshotting in the future. And so, yeah, just to summarize, the kind of like key performance win here is that you're skipping all of this like JIT compilation type work like CUDA graph capture and the torch compiler, which takes up a lot of time when you're spinning up an inference server. These things are super critical optimizations for performance. It's like a factor of 5, a factor of 10 on your actual inference performance if you try to like just skip these steps, since they're technically optional. But it's just like, it's such a killer for your actual performance that you like absolutely need this when running a practical inference server. Yeah. So let me just check a couple of these questions in the chat. SGLang spin up faster than vLLM. I would say vLLM defaults to using torch compile, and that's part of how they achieve, their like support for a wide array of models across lots of hardware with really high performance. SGLang does not include torch compile, so often SGLang start is faster without snapshots. With snapshots, they should be around the same. And the question from Yash Smith, saw Modal's post about 5 to 12 second cold start for Gemma using GPU snapshots. Can you clarify if that is a strict time to first token metric? Full process of spinning up the snapshot container and generating the first token. I think the 5 to 12 seconds there is probably just like time to 200, so time for the server to start. Time to first token is going to depend on like how long is the like prefill on your first request, how many requests come in, but it will add probably a couple of seconds on top of that. So I haven't focused on it I haven't focused on then the like application layer notion of what it means to like service a request. I've just been focusing on like here how long it takes to like get the application into the state where it can accept a request and start servicing it, because that's sort of the main thing that we have control over and can help you with in Modal. Zach's question: do you have a plan to open source the support for vLLM and SGL? Like, there's no real magic sauce here. Like the vLLM and SGLang support, like you can check out our examples to see how it's done. It's built on top of the components of vLLM and SGLang. And yeah, so there's nothing really closed source. All the part that I guess is closed source is like how we map the snapshots onto our cloud sort of like storage system, the like cloud native cache system that I talked about. But that is like more like sort of a performance thing. And, if you're interested in implementing that, you can check out what we and others have done on this kind of snapshot restore. I think, it's plausible. We've open sourced components of our system, like our virtual proxy layer and others in the past. So it's plausible we eventually open. Oh yeah, also the CUDA checkpoint support right now some of it is actually, the code for it is inside of the Modal client. So you can find it there. So question for Vlad: we use warm up the models a few times at startup. Do we need to warm up after restoring GPU snapshot, or it's already warm? In general, you should need to warm up after the GPU snapshot. It should already be warm. And so you should move all of your sort of warm up work into the snapshotting phase. Question from Frank: what workloads still do not snapshot well today, and why? There's a couple of things. I already mentioned that like multi-GPU and multi-node support is relatively limited due to like what the underlying driver support is, and also it's like honestly a hard problem. Like Nickel is the like communication model of Nickel is not amenable to snapshotting, unlike sort of like the GVisor cooperative preemption model. And so it's actually quite difficult to snapshot those things. Yeah, they're working on it. Then the other piece is like the snapshot does not speed up model weight loading, because in the end, the snapshot is still take some bytes that are stored somewhere and load them somewhere else. So there are some ways where we have like a little bit more control over a snapshot. But like in the end, you're fundamentally limited by the throughputs of things like, blob storage, and like model weight loading is, not something where it's not like the JIT compilation where the snapshot allows you to like, fast forward in time, right? And skip, sort of skip work. So the solution here, we're thinking about solutions to this. There's some like proof of concept stuff out there, but the basic solution is more caches that are maybe specific for model weight loading that you opt into in user code. Some like RDMA solutions, peer-to-peer sharing of this stuff. It's pretty hard to do this at the sort of like global scale that we operate on Modal, where we want it to sort of like, we want to be able to schedule your work on whatever GPUs are available all around the world to give you really excellent capacity and sort of like, always service your container starts out of the buffer. But like, it's pretty challenging to do this kind of like model weight sharing at, global scale any faster than, the speed that you get from like a fast Ethernet connection of like 1 to 2 gigabytes a second, which you already operate at. And it's particularly hard with RDNA to handle like dynamic world sizes. So these are not hard blockers. They're just, the sort of thing that means, we have this existing GPU snapshotting, and we're working on approaches for model weight loading as well, which could then, sort of speed up this last piece on model loading by, another factor of 2, 4, or even 10. So that this, and to be clear, that like model weight loading time ends up being the like dominant time for something like a like trillion parameter MOE. And turns out there are now some like really nice open source or open weights trillion parameter MOEs people want to run. So working on that now. So yeah, We're over time. I mean, it's a webinar, right? I don't have anything immediately after this, so I'm just going to keep going. And there is a recording, so if you want to, if you have to drop off, like go ahead and you can catch the rest of it in the recording afterwards on Contrast or on YouTube. But I'm going to spend like maybe 5 to 10 minutes finishing this up and then answering some questions. So first, just want to talk about what running this checkpoint and restore on for GPUs on Modal looks like in practice. We've had CPU snapshots for about a year and have done several million CPU process restorations on the basis of on the order of tens of thousands of CPU snapshots, which results in about on the order of hundreds of thousands of wall hours, and this across a couple hundred different organizations or users on CPU snapshots. So that's just the sort of host side checkpoint restore. For GPU snapshots, they're a little bit newer. We've had them, I guess 6 months GA is not quite right. They're technically still GA is a term that you could try them. Like there's no need to talk to sales in order to use them, but they are still in, I think, beta. But they've been usable for on Modal for users for 6 months. And that has led to the restoration of on the order of 100,000 GPU contexts across on the order of 10,000 GPU snapshots for a similar number of different folks, a couple hundred different organizations. And these are all numbers from maybe 2 months ago, month to 2 months ago. So the use cases for this sort of stack of optimizations, the custom file system makes cloud native development. So, Modal run, Modal shell, really quickly spinning up a container makes that super easy. So that's something a lot of people that we encourage folks to use Modal for. It's Modal's not just for deployment of your end product infrastructure. It's actually really great to sort of develop against. And Modal notebooks are built on top of this system and give you, in my opinion, a really excellent development experience, maybe the best development experience you can get for 8 B200s running in the cloud. Maybe even for 1 B200 running in the cloud. There's not that many places you could find a B200 notebook. The CPU snapshots are particularly useful for people running sort of data processing pipelines where maybe they have stuff they want to do on the CPU to enrich, process, munge some data, do some ETL. So they only need the CPU snapshots. For GPU snapshots, we've seen a lot of uptake on that for what I would call small to medium models. Anything at the scale of 30 billion parameters and less fits on a single GPU. And the torch compile, CUDA graph capture, this kind of overhead really dominates for, a billion parameter, 8 billion parameter model, something doing, document processing, speech to text or text to speech, and the sort of smaller multimodal or language models like your Quentin 3.5, most of those models, the Gemma 4 models that just came out, Ministral, all that kind of stuff. We have a case study about a particular customer, Reducto, who used this. Reducto does document processing. So an enterprise shows up and they want to index this unstructured data from all their documents, emails and random PDFs and all this stuff. They want to take that, structure it, and make it amenable to use by AI agents or ingestible into a database. Maybe you may have seen their Gmail where they ran the processing for the emails of international criminal Jeffrey Epstein and sort of indexed it all using their system. So this application runs on Modal, the GPU part of it, and they use GPU snapshots to cut latency by 70%, allowing them to rapidly burst into 1,000 GPUs in order to service these large dumps when a bunch of files all show up at once that somebody wants to process. And they're processing millions, that number's old, so probably way more than that, documents per day on GPU snapshot backed Modal serverless application. All right, wrapping up. So the overall goal in this talk was to sort of explain how we take like a process that can take like 2 kiloseconds and get that down to actually much less than 0.3 kiloseconds. That's before we add 0.3 kiloseconds, 300 seconds. That's 5 minutes, and yeah, so it actually should be 1/20th of a kilosecond here. So we wanted to walk through how we got to sort of shrink that down. And the reason, performance engineering is fun, making computers go fast is fun. But the reason why we do this is in order to make it possible for users running their applications to only pay for the hardware that they're like currently using. And so to match their sort of like provisioned set of hardware onto the like demand that their application has for that hardware, for that for that computing power. And this is particularly important for inference applications, which have this like much less predictable, more variable demand than training. And inference applications demand this much more expensive, much more like complex like hardware setups than like a previous generation of highly variable applications. And so that's what we're trying to build here at Modal. We're trying to build the infrastructure for compute-intensive applications like AI inference. So this is our little diagram of our system that we use. So today we walked through this custom runtime that's optimized for cold starts and file loading. We talked a little bit also about capacity orchestration because that's how we set up that buffer. But yeah, that's this sort of bottom layer of the modal system that helps people build all the things that they build, whether that's document processing like Reducto, music generation like Suno, vibe coding applications like Lovable, or any number of other things that people are building with this sort of new generation of generative media, generative intelligence powered applications. So yeah, if you're if you're interested, check it out, modal.com. If you are interested in building a system like this, by the way, check out modal.jobs. We're always hiring performance engineers from the like GPU kernels to the Linux kernel, and on all kinds of different systems and platform engineering. Yeah. So thank you very much. I'll answer a couple more questions, but obviously, you're not being detained. You're free to go. I'll just answer a couple more questions. And reminder, yeah, recording is available if you want to check it out. Let's see. Okay. Varu asks, is there any working example on using these optimizations? Yes. Check out modal.com/docs/examples, and you can find some pretty thorough examples for SGLang and vLLM. And then and you'll also see some like general advice in our guide on how to implement it for other things. Frank asks, is Snapshot tied to one host or can be shared across hosts? So yeah, they're shared across hosts. That's really important so that like your future, sort of boots don't need to go through this like work when you start them up on another host. That's why they have to be like stored in our cloud storage system. It is tied to like one snapshot can't be used across like every single machine in our fleet. For one, there's like different, if you're using different GPUs. But also different CPUs. Like different CPUs have support for different instructions, and so like the like and sort of slightly different shapes, and so the like raw memory representation can't always be ported. And so you'll see that as when you start when you create a new modal application, when you do new modal deployment with snapshotting, you'll see the like several snapshots need to be created, and then over time you'll occasionally see snapshots being regenerated as like new machines come into our worker fleet, or as we update and make security improvements on the like underlying security patch for the underlying operating system. Well, yeah, that's going to change things about the binary representation. We need to recreate the snapshot. So then, is it a question from David? Is it possible to also get the benefit of these improvements using AMD GPUs as well, or only NVIDIA? We only run NVIDIA on Modal right now. Like fundamentally, we can run stuff with Linux containers, and we can run all kinds of sort of things there, including AMD GPUs if we want. Used to have Trainium, I think. Yeah, we just haven't we haven't seen sufficient demand and supply to do AMD GPUs yet, but there is increasing interest over time as AMD improves the quality of their hardware and the quality of their software stack. So watch this space. Of course, we would have to figure out a way to do checkpoint restore, which I'm not familiar with AMD's solution on that front. Yeah. Let's see. Zach, if you have a standby GPU buffer, probably do the CUDA checkpointing preemptively on this buffer, which could in theory reduce the start time further. Yeah. So if you use buffer containers in Modal or min containers, one of these ways to have an application level buffer, then the CUDA checkpoint will already be present. Some love from Josh on our developer experience. Thank you. And let's see, question from Daniel, is there any difference between inference and training on Modal, or is the API the same? I think that was sort of maybe motivated by this diagram. So yeah, I'd say inference and training are, in the end, they use the same underlying Modal primitives, functions, and sandboxes. They're really just things you can do with Modal. So training has a bit more emphasis on distributed file storage with writes and reads, and inference and training maybe has more hyperparameter map type stuff, and inference is more about serving web requests. Just some stereotypical things about those, but we have all of those features in in Modal functions, and so there's no deep difference. It's really just inference, training, batch, agents, notebooks. These are all things you can kind of build on top of Modal. I guess the one exception would be notebooks, where you can make your own cloud notebooks on Modal. I think Marimo did that, but we also have Modal notebooks as a product, but for inference and training are just things you can do with Modal. Let's see. Varu asks, are there any examples for CUDA graph capture, torch compiler, and KV cache dumping? Yes, that is exactly what the SGLang and vLLM examples demonstrate. They demonstrate how to do checkpointing and restore with GPUs for these very much practical cutting edge open source inference engines. Cool. All right, it's we're pretty far over time, so apologies for holding you late, or you're welcome for giving you extra content depending on your preferences here. If I didn't answer your question, you can find me in the Modal Slack, modal.com/Slack. And I'm happy to answer any questions related to what we talked about in this webinar. I will not answer any questions that you have about free credits or what have you. For that, you'll have to talk to our support. But you can find information about Modal's credit grant programs for startups, for academics, and others on the Modal site, modal.com/partners, modal.com/academics, modal.com/startups. Thank you so much for coming, Shayan. Thanks for the kind words. And yeah, I hope to see you all again soon, maybe at some of our events in San Francisco or New York or Stockholm, or on Twitter, or at a future Modal webinar. Thank you so much for coming. Take care.